So what I want to do here is that I want to go in and I want to review. Okay. And what I want to review here is that what you're seeing here is that I said that there are really three things that we sort of like have to master with capacitors here. And I'm not going through all the details, of course, but what you're going to see here is that the three things that I really want you to know is that I want you to know that capacitors act like shorts when they're completely uncharged, and they act like an open circuit when they're fully charged. So I can literally replace a capacitor by a short at t equal to 0 plus, and I can replace the capacitor at t equal to infinity with an open, and then do calculations. Then I said that there is sort of like an Ohm's law for capacitors, and we start with the capacitance equation, and then we take the derivative of that, understanding that only the capacitance is what's constant. So then the current and the derivative of the voltage with respect to time then gives us the capacitor equation. So whenever I say in the future capacitor equation, I mean exactly this equation. This is which, and you're going to see, you're going to use this a lot, just like you may use Ohm's law a lot when you're talking about, series reduction circuits in calculations. Now, so the capacitor equation is really the most important thing in this chapter. The second most important thing is the initial conditions of a capacitor. And what it says here is that the voltage of the capacitor can't really change instantaneously. And what that really says here is that the capacitance, and you may have learned this in your 4B class, the capacitance is almost like an inertial type property for charge. You can't get rid of charge very quickly on a capacitor. And because of that, there's this lag time, is that there's, you could say that capacitance is like the inertia. And because of that, the voltage can't change. However, the rate at which charge flows can change instantaneously. And you're going to see that there is actually a discontinuity in the current of the capacitor. And a lot of the times where we see this discontinuity is because we're talking about specifically of, across resistors. You'll see that resistors that are in series with the capacitor, their voltages will jump discontinuously. And it's really because it's the capacitive current that's really changing. So what I want to do here is that I want to go in and sort of like play around with this a little bit. And one of the things that I got to do almost immediately is that I got to start building the mathematics in you. I got to build a thicker skin on mathematics, because you're going to see that there's a lot of math that's going to be coming your way here very soon. So what we can do here is that to lead you up to an example that we're going to be looking at is that one can look at how the voltage builds up on a capacitor using the capacitor equation. And what I mean by that, if you look at this guy, what we can do here is that if I solve this thing for the voltage, what you're seeing here is that the voltage as a function of time is going to depend initially on whether there was any voltage already on the capacitor here. So in other words, if you have some amount of charge on a capacitor, of course it has voltage. So this is really the initial. So if I have an uncharged capacitor, then of course this is 0. But I could have charge on a capacitor initially, right? Because if I have a capacitor, one of the things that you find here is that a capacitor will hold on to charge as long as it doesn't go to dielectric breakdown between the two ends of the wires. And what I mean by that is that if you look at a capacitor, and let's say this is the case here, and we have two wires. So let's say that this is the positive terminal and that's the negative terminal. So what we have in here, what you find here is that this is a charged capacitor. And so a charged capacitor, of course, has voltage on it. So this capacitor will hold on to that voltage or to that charge. The only way a charged capacitor cannot hold on to the voltage is that between these two terminals, if the voltage between the two terminals equals the dielectric breakdown, voltage, then what happens here is that you get arcing. And you'll get, the air becomes a conductor, and you'll literally will get a spark out of this situation. But the vast majority of capacitors don't do this. And so if you don't have these super, super high voltage capacitors, then it's going to hold on to that initial voltage. So then if I keep doing this integral here, then what I'm really doing here is that this is a definite integral. There are two things here. So how that charge builds up on, how the voltage builds up on the capacitor then is literally about this term here. So this would be the voltage accumulated between, our interval. And in this case, the way I've defined the interval is between those 2 points right there. So this is what we want to do. We want to look at something like this here. And so what you're seeing here is that I have this example right here. And I want to apply that equation to this example. So what you have here is that you could see here that we're looking at the voltage across the capacitor, which is a 0.1 farad capacitor. And you could see that I have a current source that's in series with the capacitor. So clearly the current of the source is going to tell us how the voltage of the capacitor is going to, build up charge on the capacitor and therefore build up the voltage here. But check this out. There's an initial voltage here. In other words, that voltage is low enough that the capacitor can hold on to the charge that it has without creating dielectric breakdown. So that being said here, you could see here that the current source is linear, then it goes to a constant, and then it instantaneously drops down to 0. So let's look at this thing here. So what we want to do here is that if I look at this guy, one of the things that you see here is that our capacitor equation for the voltage tells us that it's got to look like this. So there's some initial charge or initial voltage, and then there's a turn on time at t equal to 0, and then it's got to look like this here. So what you're seeing here is that when I look at the current source, it's the same as the current of the capacitor. And you could see here is that there's two intervals. So what you're finding here is that at the interval between 0 and 1/4 of a second, you could see that we have a linear term. So check this out. If I look at the slope of this equation, we could see that the slope of this guy looks like what? Well, that's got to be 4 because I got 2 divided by a quarter. So no. What am I saying?
8.
It's got to be 8, right? Right? 2 divided by a quarter should give me a slope of 8. So I know what that current source is looking like. So if this is a slope, you could see that this slope is 8. So I could see that the current in this case here is going to be 8t, in this case, amps. And then you could see that from a quarter to half a second, it's now a constant and it's a clear 2 amps. And then, of course, anything greater than t equal to 0, t equal to half a second, there's going to be, the current goes to 0 here. So maybe I should put that in. So if I move this up here, and I could come in here and I could just say for t greater than half a second, we see that this is now 0 amps. So now I could go in and I can look at these intervals. So what I should say here is that when I look at this whole equation, what I'm seeing here is that the voltage built up on the cap is then going to be, well, what's the initial voltage of the cap? So here, it's at -4 volts. And then I see that the capacitance is 0.1, so 1 over 0.1 has to give me a value of 10. And then I'm going to integrate this guy, and that t is going to tell me the range that I got to be looking at of the source of this thing. And that's how I'm going to get the voltage of the cap here. So what I'm going to do here is that I'm going to go look at those 2 time intervals. So let's go do that. So the first time interval, that what we're seeing here is that, of course, has to be time interval number 1. So what I'm going to see here is that, so the first thing is I'm going to look at the time between a quarter of a second. So if that's the case here, then I know that my source here has got to be AT. So then I'm going to write that VC of t is going to be -4 plus 10. And then my current is AT, and between 0 and t, and remember t cannot exceed 0.25 seconds, I'm going to get this guy right here. Now, if you look at this guy, what you're going to see here is that, of course, I'm going to integrate this thing for some arbitrary t that's less than 0.25. And so if I integrate that, clearly, if I look at this guy, I'm going to get, and of course, I'm going to get t squared over 2. And then that's going to be between 0 and t. And if I punch that number in, you could see that when I put 0 in, it's going to kill the second term. Maybe I should do this. Then I should get what? That looks like -4 plus 40 t squared. Okay, so that's what the voltage is. So just as you're looking at this thing, I could look at this at a couple of values if I want. And so what I'm seeing here, just to give you a sense of what I'm talking about, well, does this solution make sense? Well, what happens at t equal to 0? So if I plug that in, clearly, in this case here, I'm going to get VC of 0 is then going to be -4 volts. Not a surprise. You know, one of the things that we should look at, though, what happens in this situation? If I have, you know, half of this thing, right? Half of this thing is going to be right in here. What voltage would I expect at this point here? So if this is 1/4, then this should be 1/8. So if I look at 1/8 of a second, You know, if this is anything to scale here, this looks like it's going to be a little over 2, but that can't be right. So if I look at a time of 1/8 of a second, if I punch that in, I'm going to get a value of minus 3.38 volts. So what you're seeing here is that I go from 0 seconds to 1/8 of a second. I'm seeing that the negative voltage is decreasing. Or else maybe I should technically be saying that it's increasing because it's approaching 0. And when I get to 1/4 of a second, oh gosh, this is the current. This should never be the same. But that's essentially what I'm looking at. I'm looking at the voltage at this point, but for some reason I was thinking that I was plotting voltage here. And then as I continue to charge, you could see that when I get to 1/4 of a second, right, in this case, this is going to be at t equals to 0.25 seconds, that in this scenario here, you're going to get a value of minus 1.5 volts. So you could see that as charge flows onto the capacitor, what I mean is more positive charge, you're reducing the amount of negative charge on that. So that answer makes sense so far. Now let's go to the second interval. So the next interval should be 0.25 to up to half a second. So clearly, I'm now at a constant current here. So what's actually happening here? Well, that constant current is higher than any other current at this time. So what we would expect here is that you would have a faster drop or a faster growth of positive charge. So then if I look at this guy, so let's look at that. So now I'm looking at what? Between that interval. What's the initial voltage of the capacitor? Well, the initial voltage of the capacitor is not -4 anymore. It's -1.5. So I have 1.5. That's where it's starting off. And now what I'm doing here is that my limits of integration now are starting at 1/4 of a second. So when I look at the slope of this guy, as we already talked about, it's just a constant 2. So if I integrate this guy, obviously it's a fairly straight integral. You could see that it's going to be 2 times the difference between the time and 2 1/4. So if I simplify this as we talk here, this should be 1.5. And then there's going to be 2 times now. I'm sorry, there's going to be 2 constants. There's going to be the constant where it's 20 times t. And then I have the 1/4. So I'm going to get a second constant, which is then going to be minus 20 times 0.25. So these 2 constants are going to add, and what you find here is that you get 20t minus 6.5. So now that's the voltage of the capacitor here. And again, if we check these numbers, I could see here that if I look at this guy, what am I actually seeing? Well, if I plug in 0.25 seconds, I better get negative 1.5 volts. And I do. And I better get that. Now, because I have a higher current, I would expect a bigger change in the voltage of the capacitor. So if I go for another 1/4 of a second to 0.50 seconds, you're going to see that there's a bigger jump. And if I just plug in my numbers, I get 3.5 volts. So right away, what you're seeing here is that that's what I would expect for the voltage here. And so the last thing here is that what happens in this last case, where if I look at t greater than 0.5 seconds? Well, what we would expect here is that the current source drops to 0. So that means that you have no more flow of positive charge. And once again, because capacitors, right, they don't discharge under normal situations, what you're going to find here is that now what we expect here is that we expect no change in voltage. In other words, VC at 0.50 seconds should always stay for this guy right here. It should always remain at this spot. Now, if I look at the equation, of course it has to say that, because now let's go look at this. So if I look at VC of t greater than 0.5 seconds, it's got to be its initial voltage. What's its initial voltage? It's got to be 3.5. And then I get 10 between 0.5 and t. And what's the current? It's 0 times dt. And of course, if there's no current that's going to flow, I'm always going to have 3.5 volts. So that's exactly what we expected. So, and mathematically, that's exactly what we're being told about the capacitor here. So in summary, we have three intervals. We know that the voltage of the capacitor has to look like this here. It has to be minus 4 plus 40 t squared. And this is between in a quarter of a second. And then I have 20t minus 6.5. And that's got to be between a quarter and a half a second. And then finally, this guy remains at 3.5 forever for that. So here we go, right here. So that's what that is here. So to finish off capacitors, one of the things that I should, just briefly talk about is that I want to go in and remind you what we said about resistors here is that if we look at the resistivity definition of resistors, and when I say resistivity, I mean something very specific. That means that if I look at the resistance, it should be the resistivity times the length divided by the area. And so what we find here is that if I look at the property where R is proportional to L, what this tells us here is that as I add resistors in series, we increase length. And so as we increase length here, what this tells us here that R series must be then R1 plus R2, etc. If I look at just the geometry of resistance, when I look at the area here, what we find here is that as we add resistors in parallel, what do? We increase area. And because area is in the denominator, then we write our parallel as the inverses of the resistance. And it's all because of how we define the resistance with the resistivity and the geometry. Well, guess what? The same thing happens with capacitors. So if you look at all capacitors, capacitors just like resistors, there's a material dependence. For resistance, it was the resistivity. Then there's the geometry dependence. For resistors, it was length over area. So what you find here is with capacitance here, if you look at the capacitance of parallel plate. By the way, I do not have to do this with parallel plates. I can do this with cylindrical capacitors. I could do this with spherical capacitors. I could do this with any kind of capacitors that you want to talk about. And what you find here is that this capacitance is equal to, check it out, assuming that we have no insulator, just air, we have the, instead of the resistivity, we got the permittivity constant. And then here's the geometry part. It's area divided by the separation between the plates. So check this out. C is directly proportional to the area. How do I increase area? Is we have to put things in parallel. So when I put things in parallel, this tells us here is that as we add caps in parallel, because they're in parallel, what do? We increase area, not length. So guess what? In this case here, we find that capacitors in parallel, they add directly, the opposite of resistors. And if I do the same thing here, what happens if I add things in series? Then the capacitance is proportional to 1 over the plate separations. So that means here is as we add caps in series, what do? We increase length. You know, if we had more time, I could go in and draw pictures, but maybe that's an office hour type thing. So what this means here is that it's the inverses that we add capacitors when they're in series. So these are things that you're going to have to pay attention, because sometimes these guys make calculations easier if we can add things in parallel and series to get one effective, capacitance value. That being said, let's move on. Here we go. So I'm going to reduce my discussion on inductors. So now we want to talk about inductors. Now, I'm pretty sure last semester you guys covered, Faraday's law, because me and Marcus were talking, and yeah, he told me that you guys did. So now that you guys are local experts in inductors, let's just briefly talk about them. So the main law that governs inductors. So maybe the question we should start off, what is an inductor? Well, an inductor is really any coil, right? So it's any coil or solenoid. I mean, they're really the same thing. Okay, so it just depends on how you wire these things, right? And you typically don't deal with the single wire, because typically single wires, you'd have to put a lot of current in there to really measure something. So typically you have multiple turns in order for that to happen. So the law that governs inductors is Faraday's law. Right? The beautiful Faraday's law. And when you look at Faraday's law, what you find here is that it says this. It says that if one changes the magnetic flux, and the way we define magnetic flux is typically with the symbol B here. Hey, by the way, why do you think they used B and not M for magnetic flux? And it's all historical. Just like, why is it that we talk about positive charge flow and not negative charge flow? It's all historical.
Because they messed up in the past.
Yeah, I mean, the guy, a lot of times they put the blame on, like for charge, for example, they put the blame on, Benjamin Franklin, but they don't realize that you got to go further back. You got to go back to Volta, the guy who really figured out how to create a power supply. He's the one that really set, the convention. It turns out that the reason why they didn't use M for magnetic fields is that M was already in use. So they had to use a different symbol. And the next obvious choice was B. That's why they use B. So if one changes the magnetic flux through, through I'm going to say a circuit in induced voltage, which they typically write VL, is created. Now, I'm not going to try to go in and try to explain physically what we mean by that. But one of the things that you want to pay attention to is that we do the following thing here. Is that what we say here is that anytime you change the magnetic flux through an enclosed loop, you typically saw this guy as V induced. But any circuit is an enclosed loop. And this is what we call the voltage of the inductor. Now let's be careful. What do I mean by a circuit here? So you could imagine that I have a power supply. And let's say that we have a switch here. And we have some load in the circuit. Now note that this load can be complicated. And what I mean by complicated, it could have capacitors, inductors, resistors. It doesn't even have to have an inductor in the circuit. But check this out. As soon as I close this switch, what you're seeing here is that I have an enclosed loop. And so what's happening here is that you're going to see that there is current flow in the circuit. So now, because there's current flow in the circuit, what you're seeing here is that there's now a magnetic field that's being produced. So if I look at the current right in here, what you're seeing here, now note that this current here is changing in the circuit. And because it's changing, what you're going to see here is that you're going to have a field, magnetic field, that's going to do what? It's going to wrap around into the loop. And as it wraps around into the circuit here, this is what they call self-inductance. And I'm assuming that you guys talked about this to some extent. How much did you talk about it? I have no idea. But that's what we mean by Faraday's law. So what I want to do here is that this is the governing law of all inductors right here. And this guy is very, very, very close to the inductor equation. We talked about the capacitor equation. You'll see that this is where I'm going to derive the inductor equation. So just to remind you of what we actually mean by this here, is that it says this here, that the current flowing into that loop is going to induce a magnetic field that's going to oppose the change. And so what I'm saying here is that this induced voltage, but typically they call this an induced EMF, right? EMF is a voltage term, even though they call it the electromotive force. It's not a force, right? That's the most hideous name for an induced voltage. Wow. So now we don't even say, electromotive force. We just say, no, we're going to call that an EMF. So we don't confuse people on what's actually happening here. But this induced EMF or this induced voltage, which is what we call them in circuits, induced voltage, is clearly, the most important thing in our society. We generate EMFs in order to operate our society, right? And everything from power supplies, even to the chemical EMFs that are created inside the battery. It's the most important thing here. So what I want to do here is that I want to go in and I want to start looking at this thing physically to show you why there's a minus sign. And what I want to do here is that I want to give you an example of this to try to shake off the cobwebs, about this whole thing here. So what I'm going to do here is that I want to introduce the induced voltage. Maybe I should say the induced EMF for a little bit, but we want to get away from that because that's not the way we talk about it in circuits. With a magnet approaching a closed loop. And so what I imagine here is that I have a closed loop. So what I'm going to do here is that imagine that this is my closed loop right here. And, maybe even though I'm saying a loop, what I can do here is that you could imagine that maybe I even have wires. Okay, so this is a top view, if I could say this, or a side view. Okay, maybe I should say that this is a side view. So this is a side view, just to make sure that we're clear. So if I'm looking at the side view, what I'm going to do here is that I'm going to set up a magnet. So here's my magnet. And of course, this is a dipole magnet. And when you're looking at a dipole magnet, we typically define the red as the north end, the white as the south end. And what we're going to do here is that we're going to send this guy in. We're going to move this towards this enclosed loop right here. So what actually happens here? Well, what happens here is that there's a series of things that happens. So what happens is that there's an increase in magnetic flux into the loop. Now, how is it increasing? Well, what you're seeing here is that I'm seeing more north field into the loop with respect to time, right? I'm seeing more north magnetic field in. So when I look at this thing, I'm going to draw a picture and I'm going to say that as this thing is moving, what's going through here creates an increase in the magnetic field. And that magnetic field is due directly to what? To the magnet. So therefore, I have B increase. That's what I mean by this guy right here. So therefore, I have B increasing. So according to Faraday's law, if I have an increase in magnetic flux, then the coil with its self-inductance is going to produce a field that's going to oppose this change. So in other words, Faraday's law tells us that there's going to be an induced magnetic field in the opposite direction. So the question is, what creates a magnetic field? So then we say then that the enclosed coil creates an induced magnetic field that opposes the change. And this is what we mean by be induced. And so what happens is we now ask the question, what creates a magnetic field? And we all know what creates a magnetic field is a current. So this implies here that then this be induced must be proportional to some induced current. So what is the direction of the current here? So now using the right-hand rule, we come in here and we say, using the right-hand rule, we determine direction of current flow of I induced. So if I look at this thing, I could using my right-hand rule, what this tells me here is that the current must be doing what? It must be moving in this direction right here. So this must be the direction of the induced current. Now what we find here is that how is this induced current related to the induced voltage? Well, just by as anything else, anything that creates a current must have a voltage. So that tells us here is that I induced must be proportional to V induced. But we don't call it V induced in circuits. We call it VL, V of the inductor, V of the self-inductance right here. So what we do here is that we now change the picture. So the true picture is that we go in and we look at our coil. And now that I have my coil here, what you're seeing here is that we come in and we draw a power supply. What creates that current? That current then has a power supply now. And it's a positive, negative, and it's this induced voltage, right? That then is going to produce this induced current. And that's what we mean by this induced voltage here. So that's what Faraday's law. Could I go into more detail? Yes, but I'm not. And what I want to say here is that we have a lot of similar properties here as before. And what we do here is that we're going to say the following thing, is that I talked about three properties before. I then want to say that there are three properties of inductors that we'll summarize. The first thing here is that I think I should probably start out with the Ohm's law for inductors. I think it's going to make more sense. So I want to look at Ohm's law for inductors. Well, what we find here is that this is what we really mean here. Is that, so if we start off with Faraday's law, what you're going to see here is that we say that the inductor voltage is going to be minus the magnetic flux, the rate of change of the magnetic flux. So what we do know here is that flux depends on what? So what this tells us here is that flux depends on the magnetic field. I'm sorry, let me do this different. It depends on the number of turns of the inductor. It depends on the magnetic field. And of course, it depends on the area. But what we know here is that in order to produce a magnetic field, it has to be proportional to a current. So when you look at this whole thing here, this whole thing must be proportional to the inductor current. And what do we call the inductor current? IL. So you're seeing that there's a proportionality constant, right? So what we find here is that there's this proportionality constant. Let me write it over here. So this tells us that there must be a proportionality constant. And this proportionality constant, we lump in all of these things here. They depend on, it's going to be a function of what? It's going to depend on N. It's going to depend on area. It's also going to be 10. So, and it's also going to depend on the material. So look what you're seeing here. So I should be more careful here. I left something out. It also depends on the length and material. So what you're seeing here is that you have a piece of this from Faraday's law here. This is telling me about the geometry. And this, of course, is telling me about the material. So check this out. Let's go back up here for a minute. Look at this. This is what? Geometry. This is about geometry. This, however, is about material. And this is about material. So when we go back and we look at this, Faraday's equation, this material is then that magnetic constant. So the way the geometry is that we take all of this stuff here, and we got to be really, really careful here, because maybe I shouldn't use the symbol L. Maybe I should use a script L where this represents length. And the reason why we don't want to do L here is that this whole proportionality constant is then defined. So this whole constant is then defined as the self-inductance. And what's the symbol for self-inductance? L. So in other words, we then bring this into Faraday's law, and then Faraday's law then tells us here that VL is equal to minus dt of L of I, which is then minus L dIL dt. Now, there's this pesky minus sign. And one of the things that I'm going to do here is that I'm not going to deal with that minus sign as much as I want to. Maybe later on when we get into RL circuits, I might come in and tell you how some of your textbooks actually just plain out lie to you. And you have to use Faraday's law to actually look at circuits, but that's a different discussion here. That minus sign in circuits actually disappears. And again, I won't tell you why, but I'm going to define now the Ohm's law for inductors. And it reads like this. It says that the voltage of the inductor is equal to not minus, but plus di dt. This is the second most important equation in this chapter. And this is what I call the inductor equation. And so what you find here is that now that I have the inductor equation, I then want to change this thing here. And what I want to say here is that inductors act like shorts when they're completely saturated. And I know a lot of people will say, no. When the inductor is completely charged, well, that doesn't make any sense. Guess what? Inductors are neutral. So how could they be charged? The amount of current flowing in is equal to the amount of current flowing out, so that makes no sense. The proper word is saturated. And when you say saturated, what you mean here is that you have a constant current flow throughout the inductor. And in open, when instantly trying to change current. So that means here, if I have steady state and I have a circuit that, let's say, looks like this here, and let's say that I have something like an inductor like this here, well, this is R, this is L, and then this is the source here. What you're going to find here is that if I have a constant current, what this means here is that the voltage of the inductor, which is L di dt, is clearly zero. Anything that has a voltage of zero, that implies here, so anything with V equal to 0 is a short. So that means I could then go in and I can replace the inductor in the circuit with literally a short, because there's no voltage drop across this guy. So where the inductor is, I now has dL equal to 0. So what you're going to find here is that if now you have a sudden change in current in an inductor, let's say that you have this situation here, where maybe you have a circuit that looks something like this. Maybe you have a resistor, and then let's say that you have another resistor here, and then suddenly you have a switch. So what you're doing here is that we're going to assume here that we're going to close the switch at t equal to 0. So initially, VL, excuse me, IL at 0 minus is 0. So of course, I have some resistor 1, resistor 2, and I have some voltage source. So at t equal to 0 plus, the switch is closed and the inductor is now in the circuit here. Well, what actually happens? So if I look at the limit as delta t is very small of VL, then I'm really looking at the limit of L di delta t here. And you can see here, as this guy gets really, really, really tiny, this grows very large. And if it grows very large, that means all of the voltage drop is going to be on the inductor. And so it acts like it's going to take up all the voltage here. So if you're looking at the circuit here, what you're finding here is that if it grows really large, then the inductor dominates the circuit and no current flows, right? Because in essence, what's going to happen here is that if I look at the circuit, you're going to have it where it looks like this. I now have an inductor, and you could see here, if you look at KVL, so if this inductor voltage is huge, then that means that the voltage of 1 is going to be tiny, because what you're finding here is that KVL tells you then that V source is going to be V1 plus V of the inductor. But if this is tiny and this is large, then there's going to be, that implies here that there's no current flow through V1, through R1. It's just going to dominate everything. All the voltage is going to be across the inductor. So therefore, the inductor acts like an open. So the last thing that I want to talk about here is that I want to say here that the initial conditions for inductors read like this here. And what you find here is that the current of the inductor, let's say at some t minus, versus the current of the inductor at t plus, cannot change instantaneously, right? So this current cannot change instantaneously. Now, does this make sense here? Well, let me give you an analogy before moving on here, because like I said, I spent a lot of time on the capacitor looking at the physics of it, and you're going to see that the inductor is very, very, very similar to this. So what I want to do here is that I want to talk about a water circuit. So imagine that you have a water pump. Okay. Okay, here's a water pump. And what you do here is you do the following thing here. You imagine that you have a water pump, but now you have this pattern where the water goes through a series of turns. And you could imagine that I could have a whole bunch of these turns, but let's just, let's say that it looks like this, and maybe you have some device here, and then you start the whole process to come back here. Right, so in essence, this is sort of like your load and stuff like that. So let's kind of look at this thing here. So water is flowing through these pipes here or through this hose system. And what we're going to do here is that we want to imagine what is the current of the system here. Well, if I look at the load, what I'm really seeing here is that I have water flow coming in here, and I have water coming out of this thing. Okay, and of course I have all of these turns that are coming. Right, I have all of these turns. And what you're seeing here is that this represents the number of turns of a coil. In other words, an inductor. So what I'm going to assume right now is that when I look at the current flow here, so in this case, I have water flow. I'm going to say that it's constant here. Now, here's what I want you to imagine here. Imagine now that you suddenly change the water pressure at the water valve. Okay, so now, suppose now the water pressure is increased by the water pump. And what you do at the water valve is you essentially do what? You increase the amount of water flow that's going to flow through it, but it's really the pump that's really doing that here. Question: does the water flow instantly, how do you spell instantly? Something like this. Instantly change at the load? And remember, this is what I called the load right there. And the answer is absolutely no. So as you change the water pressure at the pump, what you're doing here is that you're sending essentially a shock wave that's going through the whole system. So what you find here, excuse me, is that the current flow at T minus will not change at T plus because it takes time for that pressure change to change because there's so many windings in this system, in this water inductor, if you want to call it that. So what you're seeing here is that because of this process, the current of the inductor will never be able to change the current quickly. However, that is not true for the voltage. The voltage of the inductor is typically not the same. So these guys, we say here, is that the voltage can change instantaneously. Oh, absolutely it can change. And that the reason why the inductor voltage can change here, okay, so the reason why the inductor voltage can change instantly is because you see that this guy is proportional to what? The rate of change of the current. So if I have a microscopic flow of current from 0 to a non-zero value, then you suddenly get you can change that instantly. And so what we're saying here is that this has the ability to sense changes, whereas the inductor current does not sense that ability, but the inductor voltage does. And so that's what we mean by that. Okay, that's what we mean by that. So what we want to do here is just to, again, keep moving along this direction and, sort of like break it up a little bit. I want to say that I'm going to be done with this inductors, and I want to go in and I want to do this example right here. So let's go look at this example. So this is example 6.2. So again, this is just a mathematical thing. And I just want to keep you moving and thinking in this direction, but you're going to see it's the next section that's the most important. Okay? It's the next section that's the most important. And that's when we start looking at initial values of capacitors and inductors with switches. So here we go. So what you're seeing in this example here is that you have a current of an inductor. We have a 5 Henry inductor. By the way, 5 Henries is a massive inductor value. You want to make sure you don't short out that inductor. Oh yeah, that one's going to hurt. So you have a 5 Henry inductor, and it's given, they're telling us that this is the current of this guy. And so what you're seeing here, even though you're not looking at this thing, T has units of seconds. Current has unit of amps. Yeah, 5 inductor will definitely put out that kind of thing. What we want to do here is that we want to determine the power absorbed by the inductor and the energy stored. So how do we do this? So when I look at this thing, the first thing that we do here is that we always calculate power the exact same way. So power for resistors is odd because resistors are linear. And so when you calculate power, you could say that the power of a resistor could be VR IR. And then because of the linearity of this thing here, you could then go in and you can write this way, or you can write this that way. That's the exception. All other devices always measure power as V times I, always. So if I want to calculate the power of a source, as we already know, it's got to be like this. If I want to calculate the power of an inductor, it's always the voltage of the inductor times the current of the inductor. And I could say the exact same thing for the capacitor. So that's the way we typically calculate power. So here we go. So the first thing that I want to do here is that I want to look at the power of the inductor, which I'm going to write as PL. So here I go. The power of the inductor as a function of time is going to be the voltage of the inductor times the current of the inductor. And what we're seeing here is that I have what? Well, I know that the current, right? So at t equal to 0, it doesn't matter. It's only at t greater than 0. We see that IL of t is then going to be 4 sine of 2t. So if I plug that guy in here, you could see here that the power of the inductor then is going to be what? It's got to be, of course, the voltage of the inductor. It has to be what? The inductance. Look at what the inductance is. It's what? It's 5 Henry. So then this should be, it should be 5 times the derivative of the current. So in this case, it's going to be 4 sine of 2t. That tells me what the voltage of the inductor is times the current of the inductor. The current of the inductor, of course, is 4 sine of 2t. So when I take the derivative of this guy here, you could see that the inside, I got to take the derivative of the argument. So I'm going to pull out a 2, so I'll get 8 cosine of 2t times 5. 8 times 5 is 40. So I should have, let's make sure I get that right. 8 times 5 is 40. So this should be 40 cosine of 2t times 4 sine of 2t. So if I clean this up a little bit here, I should then write, what is that? 160, right? 160 cosine of 2t sine of 2t. Now, what do I know about this thing here? Well, for starters here, there's a hint up here that you can use this relationship. So if I have cosine of 2 times sine of b, then this should then give me what? So then this is then going to be 80 times 2 cosine of 2t sine of 2t, sine of 2t. And then if I use the identity, right? So here I'm going to use the identity. That identity then says it's got to be 80. Then it has to be what? It has to be the sine of 2t plus 2t plus the sine of the argument subtracted. And of course, you're seeing here is that the sine of 0 is, of course, 0 here. So then what I see here is that the power of this guy is then going to be 80 sine of 4t. So this is the power of the inductor as a function of time. And of course, this should have units of what? Watts. So there's my power of the inductor. So if I want to get the energy of this thing, we still use the same mechanics definition here. So it says that the energy stored in the inductor, what do I mean by the energy stored? That is, the energy is in the magnetic field of the inductor. So the way we typically write this here is that we write this as W for the energy, which is N from 0 to T, and we integrate the power. So if I plug this in, you could see here that this is then going to be 80 from 0 to T, and then I have the sine of 4T dt, and if I integrate this thing, you're going to get a value that reads 20 times 1 minus cosine of 4t. And this tells me the energy of the inductor. Okay. So what I want to do here is that the next thing that we do here is going to be switch circuits here. We're going to look at capacitors and inductors with switch circuits here. And the one thing I want you to pay attention to is that you want to brace yourself. You remember the second question on the exam? Your job for the next 2.5 chapters is to become an expert at KVL and KCL. And a lot of the times it's like choosing the right loops, choosing what's in series, what's in parallel, and everything from really chapter 2 really comes back and haunts you right here. So now that we get there, you're going to see that we're going to be setting up 2 equations, 2 unknowns. Sometimes, so most of the time, what you're going to see here is just going to be the voltage of the capacitor and the current of the inductor. That's what's typically doing. So you're going to have to use sometimes a couple of KCLs and a couple of KVLs to get those 2 equations. And the whole goal is to do that. And you're going to see that now it has to be differential equations. So that's where we're at now. So I believe I'm going to finish this chapter on Monday. So I'm going to try to set the homework for next Wednesday. Okay? So that means if I do that, I expect the quiz to be next Wednesday. Okay, thanks a lot. Look for my email to start distributing some of the equipment, okay? I'll talk to you guys later.